Howdy, this is ECEN 214, Electrical Circuit Theory. I'm Tara Godloni, and this is
VO.
And we're going to be talking about node voltage, or KCL, today. So basically there are many ways to analyze a circuit, and today we're going to be talking about KCL. So the first step to perform a KCL is to identify nodes in a circuit. So a node, for example, if this is our voltage source right here, a node is anything that has three or more components connected to it. So, for example, this would be a node right here. And we also want to choose one node where basically the voltage at that node is 0, so that's like our ground node. So we can choose, for example, maybe a node right here to be our ground node. We know that the voltage at this node is going to be 0, and we would know at this point it's 0 because for this resistor coming down here and that resistor coming down here, all that current flow is going to come down and join all the way down here with this node, and it's going to be a potential of 0. So the next step is to label our unknown voltages. So if we go back to another circuit and we have nodes something like this, you might have a problem where you have a unknown voltage at this point, V0. So we can label this voltage as V0, but we also want to label our nodes. For example, this node is Vx. And we want to identify later on the currents leaving and entering this node. So for example, we know that there's a current leaving this battery. Let's call this Ix because it's going into Vx. So current's leaving this battery and coming into the Vx node. And then we can call this I0 leaving Vx because I0 will be supplying V0. And then we can call this down here I1. And that's how we know where current is coming in, where current is flowing out, and that is basically the basics to setting up KCL. And we can then solve the KCL by setting up the equations, like I'm pretty sure that's V is equal to IR for almost all these nodes, and usually node voltage is the best strategy for solving a circuit. So this is the first question. This is something that you could definitely see on a quiz or an exam or something like that. So the first step we talked about was labeling our nodes. So we're going to go ahead and label this V1 and label that V2. And then we also want to label our reference node. We can pick this node right here. And so this is our V1 up here, our V2 right here, and then our reference node. So now we also talked about labeling the currents that are going in and out of the circuit. So I like to do one thing where I claim that currents are leaving all the nodes. So we're going to assume that current is leaving all the nodes V1 and V2. So what that basically means is that you can visualize the current leaving like this, going there, and from V2 going there, going here, and going down, right? This isn't what's happening in reality. It's almost the complete opposite. But this is something that we can help, so it can help us simplify solving our circuit. So let's go ahead and actually try to solve this. So we want to solve for currents leaving V1, so we will talk about V1 right now. We'll set up a system of equations with V1 and V2. So we have V1, current leaving V1 and going towards this 144 volt battery. So we know this voltage at V1 minus 144 volts over 4 ohms is that current, right? We also know that there's a current flowing down into this 10 ohm resistor, and we'll call that V1 over 10 ohms. And then we'll also know that there's this current leaving from V1 and going to V2, so we know that's V1 minus V2 over 80. And we can pretty much set all this equal to 0. Now for V2, we're going to do almost the same thing. So it's just going to be this current over here going that way, so that we know that's V2 minus V1 over 80 ohms. Let's label those really quickly. Plus V2 over 5 ohms. But although we said V2 has a current going down, what's actually happening in this circuit is that there's a 3 amps coming into the circuit. So we would set this equal to 3, but in order to simplify it, we're just going to say minus 3 is equal to 0, and for algebraic reasons that all adds up. So now we can simplify this. We can solve this system of equations, and we can kind of simplify this down into something like this. If you can get your calculator to help you solve a system of equations, that would be a great help. We got this from, this is the V1 equation, and then this is the V2 equation. We simplified those down. So you'll solve these system of linear equations, and then you'd get a V1 and V2 respectively. So that's 100 volts and 20 volts. And that's it for the first question. Okay, this is the second question. It does look a little bit harder. You know, we have this little top section right here, but don't worry about that. We're gonna solve this right away. So to start off, we're gonna figure out which nodes are gonna be our most essential nodes. We know that can't be a node. This probably shouldn't be a node, and there's absolutely no node there. We do know that this is a good spot for a reference node, and we also know that since we X all the rest of those nodes, that probably should put V1 and V2 right here. Those are probably good spots for those. Oops. Right. So we're going to assume the same thing, right? Current is going to be leaving all the nodes. Okay, so if we assume that, then we do have current leaving this way, we got current going this way, and we got current going this way. That's for V1. For V2, we got current going this way, and of course, that way. So now all we have to do is just write out like one equation for V1, like we did in the last question. And we'll do this by saying, all right, we have this current here at V1, and the next voltage potential is 50 volts. So we'll say, all right, that's V1 minus 50 volts over 80 ohms. And then we'll also say there's another current going from V1 to V2, and we'll denote that by saying that's V1 minus V2 over 40 ohms. And then the last current is denoted by saying V1 over 50 ohms, which is equal to 0. now we will solve equation 2 for V2. So we know V2 has currents going this way, that way, and that way, and that way. So our first current going from V2 to V1 over the 40 ohm resistor, we're going to say that's V2 minus V1 over 40 ohms, plus V2 over 200 ohms, minus the 750 milliamps. But we're also having current flowing from V2 all the way over to this branch here, and the next voltage potential is at 50 volts. So we're going to say that's V2 minus 50 volts over 800 ohms, and set that equal to 0. So now all you have to do is just simplify the system of equations, but like I said in the previous question, you will extremely benefit if you can get your calculator to do this. So this is one equation, and then the next equation. And then you would just solve those system of equations, and you'd get to solve V1 is equal to 34 volts, and V2 is equal to 53.2 volts. Now, the question is actually asking us to solve the value of V0. So now that we know that this voltage potential right here is 53.2 volts, we know that this voltage here is 50 volts, and we assume that the current was going this way. We know that all the voltage difference is going to be is all that voltage that was dissipated, or the voltage drop across that 800 ohm resistor. So we know that V0 is going to equal to V2 minus those 50 volts. So we know the voltage drop across at V0 is just 3.2 volts, and that's the answer. Alright, question 3. This is introducing dependent current sources into what we already know about circuit analysis. So what this will mean is that you have to find out pretty much what this voltage is here, so that we know what the current value coming out into this node here is. So we're just going to jump straight into that. So we're going to label our nodes first. Let's call this V0. Let's call this V1. And we're not going to forget our reference node, of course. So we need to now basically label our currents, right? So we know we got a current that way, going this way, going this way, but in reality we know that this should be going upwards, right? This is going to be a negative sign. And then we know at this node we got current going this way, current going that way, and current going that way. Alright, so let's first equate or solve what Vx is, or let's start solving what Vx is. So in the other question we said that basically the voltage drop at this resistor will be equivalent to our V1 minus this other voltage potential, which is 4 volts. So we know that Vx will be pretty much V1 minus 4 volts. Alright? And now we can start writing questions in relation to our two system of equations here. So we know that V0 is going to be this 7 amps, because we know all the current in this branch is just going to be equal to 7. So we know that's 7 amps. Plus a V0 over 3 ohms. Plus a V0 minus V1 over 1 ohm. We're going to set all that equal to 0. For V2, oh sorry, oh god. Alright, I'm sorry, but I made a small mistake. This is actually V0, and this is V1. Okay, so at V1, we're going to have that current from V1 to the 4 volts divided by these 2 ohms. And then we're also going to have V1 minus V0 over 1 ohm. And then we're going to have this current source, remember, coming into our node. So that's going to be minus 2 Vx. We're going to solve that equal to 0. But what are we going to do with this Vx here? Well, we know that Vx is just V1 minus 4 volts. So then we can rewrite V0 as basically V1 minus 4 volts over 2 ohms plus V1 minus V0 over 1 ohm minus 2 times V1 minus 4 volts, which is all now equal to 0. So now we can just start to simplify these equations into something like this. We'll call that equation 1. And then this is equation 2. And then we'll more simplify this to here. Okay, so sorry, yeah, this is just equal to that. So all this will equal this. And then we can just solve V0 is equal to 1.5 volts and V1 is equal to 9 volts. So yes, they said solve V0 and we labeled this node as V0. So the voltage at this point will be the voltage drop across V0, because if, for example, this is 1.5 volts, our reference node here would be 0 volts. So we know that this resistor, the 3 ohm resistor, would be dissipating the entire 1.5 volts. Okay, the last thing is a supernode. What is a supernode? It's not Superman. It's 2 nodes sandwiched together with a voltage source in between them. That's all it is, and we call it a supernode because we can now treat it as one entire node. Let's call this node Vx. Alright, clearly you are masters of supernodes, and we're going to solve this question now. So first we're going to kind of approach this in a way that we've always been approaching it, and we're going to label our 2 nodes here that we're going to use anyway. So this is going to be V delta and this is going to be V0, right? So we can call this, let's say, our reference node. So now we're going to make this our supernode. So now we know that there is a voltage potential here and a voltage potential right there. So what does that tell us? Well, that tells us that the voltage potential of V0 is equal to our node V delta minus this other voltage right there, minus 5V delta. Now that doesn't always have to be 5V delta, that could be anything, and in this question it's just 5V delta. So let's start. So at V delta, we know we're going to assume now that we have this supernode that there is current only leaving the supernode. So we're going to start on this side of the supernode and we're going to write an equation for it. So we know on this side, equation 1, that this is going to be V delta minus 15 volts over 10 ohms plus V delta over 2 ohms plus V0 over 20 ohms plus V0 over 40 ohms. And all that's going to equal to 0. So there's only going to be one equation pretty much, and it's encompassing both sides. So we started off on the left side, and then as you noticed, we added current equations on the right side. So the V0 plus 20 and the V0 plus 40, because you know we can say that's all like current leaving these supernodes, right? So now it's like, okay, kind of stuck now, not sure what to do. But we can actually use this equation to our advantage. We can use this to substitute what V0 actually is. So we can only be dealing with V delta. So now we're going to rewrite equation 1 to look something like this. So that's V delta minus 15 over 10 ohms plus V delta over 2 ohms plus, and we know that V0 is pretty much negative 4 V delta over 20 plus negative 4 V delta over 40 ohms, and set that all equal to 0. Alright, so now all we have to do is pretty much solve this equation. You can pretty much plug it into your calculator and it'll spit back an answer, and we can solve V delta is equal to 3 over 10 V delta is equal to 1.5 volts, and then we can solve that V delta is equal to 5 volts. And that's not our final answer. What we're going to do is solve for V0, and we know that V0 is equal to 5 volts, which is V delta, right, minus 5 times 5 volts, which is then negative 20 volts. And that's it. Thank you.